Welcome to the first in a series of 3 webinars on functional safety management planning. Our focus today is going to be to talk about setting up the structure for the functional safety management plan and some of the common elements of it. I'm Denise Chastain-Knight. I'm a senior functional safety engineer with exida. I am a chemical engineer out of Georgia Institute of Technology. My experience covers a wide range of processes in the chemicals and petrochemicals, pharmaceutical industries. I've worked in power as well. And I have more than 31 years engineering experience in design, process improvement, risk management, and safety instrumented system implementation. I am the exida representative to the Center for Chemical Process Safety Technical Steering Committee, and I have served as the past chair of the AICHE Body of Knowledge Development Committee and for the NCEES PE Exam Development Committee for the Chemical Engineer exam. You'll note my email address is there, so if you have any questions and follow-up, you will get copies of these slides at the end, and my address is there if you want to follow up with me with any questions. So for this part 1 session, what we're going to focus on is basically the front end of the functional safety management planning and how we're going to structure it. If we start a project, a functional safety management project, and we don't have a good plan in place, there are gaps that always occur with these type projects. So we'll talk about what are some of the typical gaps that we see, and then look to how we can use the FSMP to make sure those gaps do not occur on a project. We'll talk about the planning structure, how we would set up that plan, how we would work it with our procedures and processes and our other management systems in an organization. We'll talk about some of the key contents in the policy level document, and then we will identify a number of the supporting documents that we will need for the plan. So this is a sad but often too familiar conversation. We're getting ready to start up a process, going through commissioning, and realize that there's some gaps in the functional safety assessment, that we're looking for finished products that are things people did not even know that they needed to do. So our goal is to develop a plan so we don't have this conversation. Some of the typical gaps that we see on a project that's missing an FSMP has to do with SIL targeting. SIL targets may be overstated, in which case the organization spends more money on design and implementation than was necessary. Or if the SIL targets are understated, that may mean that we have significant risk still remaining in the process that's unmitigated. We often find that the demand of the SIF gets understated. We think we have everything in a low demand mode, but don't realize the impact of multiple initiators and long proof testing on determining that demand. So in reality, there may be some high demand SIFs where the hazards are present more often, and if we're looking at them in a low demand, that too can result in a dangerous under-design. The verification and methodologies and the basis for the calculations that are used in that methodologies, the standards actually allow a number of different methodologies, but they're not all equal. Some are better for certain situations than they are in other situations. So if we're using the wrong verification methodology, we can again believe that we have a higher reliability in the system that is really existent. And of course, scope gets missed if there's no functional safety management plan. The safety requirement specification is a key core document in this entire process, and that needs to be developed following a certain procedure and protocol to get to the SRS, but then also as we go back and do verification, we have to verify back against that safety requirement specification. So it is critical, and unfortunately all too often it gets missed. Proof test procedures are something that should be developed early on earlier in the thought process. A lot of times it is left until commissioning, and then of course we find that our ability to do proof tests is not as robust or as flexible as we might want it to be. Factory acceptance testing for your safety logic solver is something that we typically would find within the quotation from that supplier, but often site acceptance testing and site integration testing with package units is something that is listed as an option, and a lot of times that does not get rolled into the budgets for a project. So again, we get down to commissioning and testing and we don't have those key connectivity tests. And then the standards require us to do functional safety assessments at periods throughout the project. If those assessments are not done, then we never know if we've come back and met our obligations or our requirements under the functional safety requirements. And then, of course, procurement. All too often we see that devices that should have been SIL certified are purchased without the appropriate certification information. So we end up having to go back and reacquire devices, repurchase to correct those issues at the last minute. And of course, if that happens at the last minute, there can be issues with installation in the field and additional rework required. So the consequence of these gaps, obviously last minute redesign, mechanical rework, safety functions may need to be added to the system that were not intended to be there initially, or the requirements of safety functions may be escalated, and all of that takes some effort to correct last minute. If we haven't made good provisions for our proof tests, there are limitations as to what proof tests could be run. Proof testing may require shutdown to do. We may not, if we had decided earlier on in the design or looked at this earlier on, there might have been a way to put provisions in to do online type testing, so you wouldn't have to take a shutdown to get those important proof tests. Package systems, typically, those that are vendor package systems, they may come with their own PLC. They may interact or be part of your safety function trip. And we have an ability, if those are identified early on, to maybe work with those package vendors and do some things that are more geared towards our reliability requirements and the SIF trips, where if we find out later on that those packages are involved, then we're pretty much limited to whatever is in the package and may have to find mitigation or risk reduction elsewhere that we could have addressed with those packages. I mentioned earlier, replacing, reordering sensors and final elements, and most critically, the biggest consequence, if we don't have a functional safety management plan and we miss these scope items, then we end up with, we fail to ensure the safety, integrity, and function of that system. So let's look at what the standard requires. This is a kind of a familiar life cycle chart for IEC 61511, and we're kind of basing this conversation on the requirements of 61511. And you will notice that we've got the functional management, the functional safety assessment, and the life cycle planning. These are going to be the two parts of this chart that we're really going to focus on pretty heavily today. As we go into the other parts, in June, we will look into the design and analysis phase and verification activities, and we'll talk about some of the things that your plan should incorporate, your plan and supporting documents to address the needs of those phases. And then, of course, in July, we'll talk about the third part of this series, the implementation, operation, and beyond. IEC 61511 has several clauses that list the requirements, and these are the ones that we are going to talk about. The general requirements, how we organize and plan, how we address the plan for the assessment and the auditing. Clause 6 gives us some specific guidelines on how that plan ought to be laid out. And of course, in the course of this activity, there's a lot of documents that are source input documents, and there's a lot of documents that we generate. So we need to make sure that that documentation is functional in the end. So the Functional Safety Management Plan, when we're talking the policy level document, it is basically the roadmap for everything that we are going to do in the safety life cycle. There's a lot of documents that are generated, and this FSMP can provide us a cross-reference for those related procedures and practices and tools, and it can make sure there is a good workflow from one step in the process or one activity in the process to the next. And then, of course, it documents what are those basic requirements, because this is a performance standard. It's not prescriptive. Owners have the opportunity to apply their own interpretations or their own guidelines for risk tolerance and risk management into this process. So you want to make sure that the owner's requirements are built into this basis. As we're developing this functional safety management plan, a really important thing we want to do is make sure we leverage it within existing quality programs. There's certain documentation, certain procedures and practices that are probably already existent within the organization. They may need to be modified or tweaked a little bit in order to incorporate them into the functional safety management. But we don't have to start over on these things. We want to make sure that all of the activities in the life cycle fit within that management program, and that they're designed in order to achieve the goal of functional safety and maintain the functional safety after we get into the operating phase of the life cycle. A lot of people will be involved. They need to know what their responsibilities are from an individual, department, and organizational level. And we need to make sure they have their competencies in line for the roles that they're being asked. So typically, as we're developing these plans, one of the things we look to is who does what. How can we extend our existing systems in order to incorporate them into this functional safety management plan? And then what procedures and processes are we going to have to develop to add to the existing management system? And of course, with any management plan, we plan what we're going to do, we execute it, and then we come back and audit and improve our processes over time. The structure that I'm going to use to discuss the functional safety management plan is this very classic management pyramid model where we start with a policy at the top, and when I'm referring to the functional safety management plan today, we're talking about that policy level document. And it's going to list some of the key basis for our design, for our system. What are the standards that we're going to apply? What versions of those standards are we applying? What are the roles for various individuals and what responsibilities come with those roles? What do they need to know in order to execute those roles and be successful? What checks? How do we check? What are the verifications and validations? How do we audit our systems? What is the workflow? How long does it take? What happens in series? What happens in parallel? What measurements and metrics might we use to check the health of the system? And then how are we going to manage all of these documents? These are topics that I would recommend go into that policy level document because they affect everything else that we do. The next tier that we would typically have in the management system is the procedural level. These are the procedures, what needs to be done, and how we're going to do it at a global level. Many of these are probably already existing in an organization: risk management plan, hazards assessment, there may be cell determination. These are front-end procedures that we want to develop and have available as inputs to the activities of hazards assessment and cell determination as we go through the life cycle, so that we make sure that the same risk criteria is applied to all projects. Proof test philosophy is important to have up front because that helps us really understand what we want to do in terms of the frequency of proof testing. Do we need to have abilities to test online, which may require special equipment in the design? Or will we be doing everything as offline testing? And of course, we need to know what our assessment and audit cycle is going to be, and what procedures we're going to use, and what criteria we're going to assess and audit against. The next level is starting to get down into more detail and work instructions. How do we do everything that we do? And these are documents that are typically developed later in the life cycle, such as individual proof test procedures for individual safety functions. And it's certainly these procedures and work instructions that we'll talk about a lot more in sessions 2 and 3. The project safety plan is something we will talk about today. We're looking to develop maybe a template project safety plan that's part of our master policy, and then for individual projects that plan gets fleshed out to document specific criteria associated with individual projects. And finally, our fourth tier is the documentation details. What forms and records are we going to keep? Something like the safety requirement specification, we may have a template or format that we define for safety instrumented function SRS in our policy level. And then of course when we implement individual projects, that document is used as the form of the record keeping for the individual SIFs in a specific application. So the general requirements, let's start there with what's required in general. There's some key words here to hang on to. Obviously, in our initial policy, it needs to be at policy level. It needs to look at the strategy of what we want to achieve and the means by which we achieve that. How do we evaluate if we've met that achievement, and how do we communicate within the organization what is expected to be delivered from the system? And it is a management system. It's not just one document that rolls out and says this is how you do it. It actually needs to integrate in with the overall management system. And then of course the goal is to place and or maintain the process in a safe state. Our planning process needs to consider what needs to be done, how it needs to be done, who needs to do this. So the planning needs to be laid out up front, and then it needs to be updated throughout the life cycle if courses needs to be corrected. And there would be some kind of project-specific plan based on how an individual project is contracted. The standard tells us, it gives us a lot of flexibility about how that plan may be put together. It can be a section of quality plan. It can be a standalone document. In reality, it probably ends up being multiple documents that work within the overall company procedures and processes. So what we're talking about today is kind of leaning towards that third approach. Clause 6 of IEC 61511 gives us some specific requirements for each step of each phase of the life cycle. We need to define it in terms of inputs, outputs, and verification activities. So you're going to see this theme more than once throughout this presentation. We're always talking inputs and what the products are of those individual steps, and then we need to stop and verify, did we achieve what we needed to at this phase before moving forward. So with that, we have to define what's the criteria, what are our techniques that we're going to apply, how do we measure that verification. We need to look to all relevant operating modes of the process, not just when we're running, but we need to look up to startup, shutdown. Are there activities such as a regeneration type system that may be a different operating mode? The process needs to look at all of those modes and consider them. When we get into installation and commissioning, the goal of this is to make sure what we have installed, what we commission, is exactly what we needed to achieve. And again, you see that line, ensure safety, integrity, and function after installation. That is the overall goal, is to make sure that this provides the appropriate safety, integrity, and then it works as we expect it to. And then, of course, the maintenance during operation. Once the process is up and running, then we've got wear and tear, so there's maintenance activities, and those have all got to be executed to assure that health of the system. And then when we are in a maintenance activity or we have instruments pulled offline to do calibration, we need to make sure there's procedures in process to manage those hazards during those activities. Some key components in the Functional Safety Management Plan. What steps need to be done? What is that sequence of activity? Who does it? How do they do it? What are their competencies? And then, of course, what is the structure and the verifications associated with each of those tasks? The Safety Requirement Specification is, again, a key document. I've mentioned that earlier. But then we have a whole series of design guidelines and methods that may support that. And then, of course, the operation, and then the Functional Safety Assessment Plan. As we're going through and doing our periodic verifications, that is a key component of it. When we look at the standards, IEC 61508 is the base standard for all industries, and then there's three industry sector versions: 61513 for the nuclear sector, 62061 for the machine sector, and 61511, which is the basis of this discussion, for the process industry sector. All have very similar requirements with respect to planning, and one of the key things we want to make sure we have in our policy document is which of these apply to the process, to the facility that we're working with, and then what versions of those standards, because most of these have more than one generation now, so we want to make sure that we note which version is in place. And of course, our current version of IEC 61508 is the 2000 edition in parts 1 through 7. And then IEC 61511, there is a 2016 release in parts 1 through 3. Once we figured out what rules we're going to follow, what standards we're going to apply, the next thing we want to look at is what is the workflow of the process. And this workflow basically follows the safety life cycle. You can break it up and add any more detail for intermediate activities. But we start, of course, with initiating a management of change, and the first thing we look at with that is what are the hazards associated with this change. We're going to use our base procedures, our core procedures, such as the PHA or HAZOP and the risk management plan, apply those to that hazard assessment, and then the output of that is our HAZOP report that's identified our hazards, and that report is part of our permanent documentation, but the content of that report also feeds into the next step of our life cycle as an input into SIL determination. So we walk through and map out the entire process in this way, identifying our inputs, our outputs, and our dependencies between the different activities in the workflow. Once we know what we want to do, then we need to look to who's going to be responsible for various parts of that. Each stage of the life cycle, there may be different responsibilities. This covers a wide range of the process. We start with process hazards that are typically operations and chemical engineering involved. Then when we get into design, obviously we're very heavy with instrumentation and control responsibility. So it takes a village, in essence, to provide all of the skill sets to address everything in the life cycle. So we want to go in and look at what departments, organizations, people, and what roles are responsible, and then make sure that they are competent to carry out the roles for which they have been charged. One way that we might do this is to do a classic RACI chart, roles, responsibilities, who consults, who supports activities, and list that out in the grid on the right, where we have the actual activities that must occur associated with the life cycle. And then, of course, we have the roles in the different columns. We can lay it out like that. And once we've defined what this life cycle requirement is and who's going to do what, then that tells us what competencies people in each role need. And competency is something where we may need to close some gaps, but your competent person will have the knowledge and the skills required to do the task, and then we may require training plans in order to close those competency gaps. These people in the roles need to be knowledgeable in the have the engineering knowledge, the training, and the experience appropriate to their task. They need to have the regulatory knowledge because sometimes we have, say, permits to operate that require safety functions in order to operate. So we need to have that kind of information as well. The requirements for the skill level, if we have a more novel or more complex type of application, there may be additional competency requirements for those complexities. And we need to define these for internal and external resources, because when we're going out with projects and we're bringing in contractors to do these activities, we have to have a way of screening the responsible parties within that contract group to make sure they meet the competency requirements as well. Just one side note, when we're looking at the competency, certificate versus certification, it's important to understand the difference between that. Competency is judged by evidence demonstrating knowledge, skill, and experience. Typically, when we go to a training class or an educational process and we get a certificate at the end of that, that means that we've been exposed to or have in some way mastered the material within that particular subject, within that particular education, but it's not necessarily a measure of overall competency, such as a certification like the CFSE or the CFSP. So appreciate the difference in those two and look for the appropriate evidence for what's required in the competency of the given role. With the program, to make sure it is continuously evolving in a positive way, it is required to do assessments as we go through to make sure that we have achieved what's required at the various stages in the life cycle. But we also want some kind of an auditing process where we can go in and improve the quality associated with it, with the work. And there needs to be procedures that basically document that. And of course, if we're doing any kind of revisions, then we pull back into the life cycle through management of change and need to apply it all over again. So the functional safety assessments as required under 61511, there are 5 of them. In the older versions of 61511, they were only required at stage 3, which is what ISA 84 says. The newer version requires all of these now. And basically it's a stop, a hold point, a check, go back and look at is the life cycle delivering what's required? And of course the team that is involved in the functional safety assessment should include some senior member who is independent of the project team. Maybe more than one, depending on the size and the scope of and the complexity of the individual project. There may need to be more than one independent. And then we need to include within our functional safety assessment any of the development and production tools that are used, which these can include simulation and modeling tools, measurement equipment, test equipment. All of that needs to be reviewed through the FSA as well. Here are the 5 stages in which the FSA is required. The first 3, stage 1, 2, and 3, are through the design and implementation process. Stage 3 needs to be completed before we actually introduce hazards into the process. Stage 4 we want to do after we've gained some experience in operating and maintenance, and there's some track record there. And then of course stage 5 would be after any kind of modification or prior to decommissioning. The scope of the functional safety assessment starts with understanding, making sure that the risk assessment was completed, because the point of a functional safety system is to reduce risk. So we need to fully understand our risk in order to reduce it in the appropriate way. Make sure that all recommendations and actions are addressed throughout the process, that we've done an appropriate change procedure. Our design, we verify the design meets the risk assessment requirements, that we have in place our maintenance and testing procedures needed to support the health of that we've appropriately validated and communicated to everyone that needs to know, as well as train people up for what their requirements are. The last point there, traceability to calibration standards. Any tools that we use for calibration or testing of equipment, we need to have that traceability so that we know that the measurement devices that we're using to check the health of the system are indeed themselves robust. Other than assessment, we may want to do some audit and revision requirements. So we do need to look into our functional safety management plan and have some provisions for doing auditing. When we get into the operating life cycle, the proof test activity is something that will be repeated over and over again for a long period of time. So it would be, we might want to go in and do an audit on our proof test procedures, how we're doing our proof tests, how we're documenting them, and make sure that that routine activity stays robust throughout the life of the process, and that we are indeed identifying failures and correcting them in the way that we should. And then, of course, we need to have a management of change in place so that if there is any change to the process, it is done within the life cycle requirements and that those are met, so we don't introduce flaws into our system. We may also want to look at some routine performance metrics that, you're just kind of doing that, monthly check-in of what the performance metrics are. And then here's some ideas of what we might want to look at: open action items, interlocks, if we have them out of service, what is the frequency in interlocks might be out of service, what is the duration, what are our as-found failure rates, because basically if the interlock is out of service or if it's failed in place, then it's not providing us, if it's not available, it's not providing reliability. So these continuing metrics give us an opportunity to look at how well we're managing those other parts of the system. Clause 19 addresses what are the documentation requirements. And certainly the reason we're doing this documentation is to make sure that the appropriate information is available, that it's well documented, so that what we have in our safety instrumented system is what we intended in order to mitigate the risk. And a big part of communication through any project is that documentation. We also need that documentation available for that verification and validation stage at the functional safety assessment, because early design documents that define the basis of what the SIS should do is what we test against when we're doing those functional safety assessments, the verification and the validation steps. So what do we need to document? Pretty much every phase of the life cycle, anything that is required to effectively perform those phases. Specifically, what is the activities, the inputs and outputs of each of those phases? The outputs are a key part of this documentation. How does that work into the management system? We will have verification documentation and validation at each of those stages where those are required, as well as the functional safety assessments. The standard does not specifically state what is required in terms of documentation, but you can kind of apply the same thought process that goes into requirements for on a PSM covered process by OSHA CFR 1910.119. What is the technology related to the process? What was our basis for doing the risk management? The document needs to suit the purpose for which it was intended. It needs to be available, accurate, understandable, accessible, and maintainable. All of those things need to be present so that people can get to the documentation, so that it's clear what is expected out of the design basis documents, as well as the verification documents clearly show results. And the documentation should be recorded in a way where it's uniquely identified through some document management system with revision control. When we get to the process safety plan, you'll see how we can actually cross-reference some of those documents so we see where they fit within the life cycle and can provide that traceability. It is important that the documents be searchable. Some of these can get quite large, and if we just simply have a non-searchable scan, then it's a lot less friendly and a lot more cumbersome information. So when we're working with vendors and you're scoping, require searchable documents. And then, of course, these documents need to be updated and amended as things change, as information changes. If there's a change in the control scheme or a change in the risk profile, we need to be able to go in and update and amend and improve the situation as it's required. Some of the minimum documentation, these are specifically identified within the standards. Obviously, the results of the hazards and risk assessment, that first step in the block. What equipment did we use? So we should expect specifications on all the sensors and the final elements associated with any kind of safety function on the logic solver. Documentation on who's responsible for doing those maintenance activities and the evidence that that work was done. So when we go out and do our proof test, we're looking for the history that the proof tests were done on an appropriate period, that the people were trained and qualified to do what they were asked to do on the proof tests, that we've recorded the as found, as left condition, that we've documented and recorded what information we've come out of the proof test in terms of what's failed, what's not, so we can look at the overall reliability. It needs to be kind of a living type document. There's a whole host of procedures that become part of this management plan that indicate what needs to be done, how it needs to be done, and when it needs to be done. And we want people to follow those procedures consistently. So if we don't write it down, we can't do that. And anything that we do to modify, revise that design needs to go through that same process of implementing and testing and validating against what the design basis is. Now this is an example of a piece of a sample project safety plan. What we would recommend is in your policy level document, you put together something like this that's an appendix that goes through the workflow of the life cycle and defines for each workflow activity what needs to be done. So we end up with a long list of the various activities. We understand the sequence in which they're done. We record what are the inputs and the outputs associated with each of those steps. So here in the template we have names of the documents. When we do a project safety plan for a particular project, we'll start introducing document control numbers into this matrix in order to track and to provide that traceability. What processes are we going to use to execute those various activities? So you can see here we've actually got a list. We've noted a document name that may be the procedure or the process that outlines the what and the why of these responsibilities and activities in the scope. And then we define who is responsible for the activity and who is responsible for the verification. And of course the keys down, the glossaries down at the bottom on these responsibilities can be adjusted and tailored to suit what your individual organization or individual project requires. We also establish these hold points. What is safety mandatory that must be done as part of the standard? In this case, the SIF conceptual design, this is where one of the stage FSAs is required. So we've indicated that hold point, and then it's a safety mandated hold point. And then we have a mechanism also, from once we have a project-specific safety plan, to follow the dates of those verifications and look at the status. This template should include entries for all required activities, but it needs to be flexible enough to coordinate those responsibilities and scopes for multiple responsible parties, as you might have in a large project with multiple contractors and subcontractors. Now, moving a little more into the details of documents, in our functional safety management program, it's going to touch onto other parts of the process that are not necessarily part of the safety life cycle, but certainly influence it. And our independent protection layers that we credit in our risk assessment is a place to look for that connectivity. You know, cybersecurity, we're interested in that because we want to make sure that the system, the safety instrumented system, is secure and that it can't be compromised from outside. Items such as independent protection layers, we may need to harmonize those with our risk management or SIL determination process. What we credit for, say, operator response to an alarm may be different where we have a well-managed, well-rationalized alarm management system versus something that has not gone through that kind of rigor and rule setting associated with targeting alarms. So we want to look to these other things that our program will connect and may need to make some tweaks or some calibrations between the functional safety management plan and some of these other processes that we might draw on because they're supportive of those functional safety objectives. Some additional reference materials that we may need to look to. I've mentioned the cybersecurity and the alarm information. Spares philosophy. It's very important that we understand what the spares requirements are on site. One of the things we use in verification is mean time to restore. We consider that. If spares are kept on site, that's obviously one time frame, but if the spares have to be shipped from, say, a central warehouse and the delivery is 2 days on that, that's a different time frame. So we need to understand what that philosophy is, and of course specific high critical spares may be treated with exceptions to that philosophy as part of our plan. There's key input documents that are going to be needed at these various stages. This is just a partial list of some of those. Most facilities may already have the hazards assessment, the risk procedure, maybe even the SIL determination procedure in place. We want the SIL verification procedure because that outlines what methods we're going to use, what assumptions we're going to use, and our basis for the calculations. One thing that many organizations develop is an approved vendors list for critical safety equipment. Go ahead and pre-approve those vendors. Then you don't have to go through a bidding process, or you just bid amongst the ones that have already met the technical bar associated with that. So that's something you might consider preparing as part of this plan. And then, of course, our test specifications for not only our factory acceptance test, but the site acceptance and the integration test. Key inputs that we want to go ahead and have pulled together in a global standpoint before we start a project. As we execute a safety instrumented system project, we're going to have different outputs come out of those. They're going to be part of our master documentation. Our hazards assessment report, our SIL targeting, was a LOPA if we did a CHAZOP. Certainly our safety requirements specification, and of course that in itself may be more than one document, and that you may have an SRS for the safety logic solver itself, and then at a different timing in the cycle you develop the SRS for the individual functions. Proof test procedures, and then of course we get from our vendors our safety manuals and our certification documentation. This is something that you're going to want to push vendors to make available early on, preferably before procurement, so that we know that what we're procuring meets our requirements, rather than waiting until items are delivered on site, get the documentation, and then find out it doesn't meet its intended purpose. And then there's other documents that are not necessarily work products per se, but certainly evidence of the activities that we've done. The test and conformity certificates associated with calibration and the equipment that comes with different equipment. We're going to have competency logs for the people who've worked in the process, or competency dossiers maybe, safety logs of various activities, change logs. There will be training associated with different activities along the way, so there's going to be training records. How do we configure our maintenance management system in order to make sure that we trigger these proof test activities when they should occur? And then, of course, what are the proof tests and what are the results of those proof tests? How are we going to log those over a period of time? And what kind of analysis are we going to do on that data to demonstrate to ourselves that the devices that we've chosen, the methodologies that we're using to ensure the health of these components of a safety instrumented function are performing to the reliability criteria that we believe they have. And then, of course, management of change. It's critical that if there's any changes made to the system, it goes through a formal management of change. So just in review, the high points for a safety management system, its goal, the reason we do this plan, is to ensure the safety, integrity, and function of the SIS. That is why we're doing all this effort. IEC 61 has specific requirements for what goes into that functional safety management plan. They are performance-based requirements, so there's interpretation that individuals can apply to your individual situation. We do want this FSMP to be part of an overall management system and integrated into the best practices of an organization. It involves a lot of documents. Some are global in scope, some are very project-specific or SIF-specific in scope. The document needs to suit the purpose of that scope. And then, of course, we must define what methods will be used, who's responsible for various activities, what are the competencies they require to be able to execute those responsibilities, and then what are the work product requirements for each of those activities. So that concludes our part 1 of this series. I would like to just remind you that we're doing part 2 and part 3. In June, we'll talk about the analysis, design, and verification activities, and we'll dig in a little deeper into the procedures and work products that need to go into that part of the functional safety management planning process. And then in July, we will look at the implementation, operation, and beyond at those phases. Just a little commercial here for some of the courses that we have. These are ongoing classes that we have, upcoming classes, and of course you can always check those out at exida.com training. And then, of course, if you have any interest in particular webinar topics, any suggestions, please send those to us at academy@exida.com. And I'm going to now go to the questions area and see if y'all have any questions. Oh, define SIT, site integration testing. What we're looking for there is if we have the safety instrumented system and it needs to connect to, say, the PLC on a turbine, we want to make sure that the logic flows and that there's a testing process that integration between those two systems occurs. Who should determine the proof test interval for different HIPS or SIL system, designer or manufacturer? Your manufacturer is going to give some recommendations for what those proof test intervals will be. Most commonly, they're going to base it on an annual type proof testing. But the reality is the owner-operator knows when they want to do safety shutdowns and what it's going to take in order to shut down and do those tests. So we often find owner-operators want longer test intervals for particularly around their safety instrumented systems because they need to test when they shut down. So it's important to know that because that does affect the overall design. If we've got a longer interval between proof testing, then there's some uncertainty, there's wear and tear, you're not actually assuring the health. You may want to look for other techniques or diagnostics that might be able to help us extend those proof test intervals. But it really does come down to be a judgment decision of when it should be run or when we can run the proof tests. And then, of course, we need to make sure that our verification process recognizes those longer periods in our calculations. Would you give an example of management of change and how best it could be done? 13849 differs from 61511. When I'm using the term, I'm sorry, there were two different questions. When should it be? Would you give us an example of management of change and how best should it be done? Management of change is, I always think of it in terms of the requirements for process safety management. Effectively, anytime you want to make a management in the change of the process, you need to go through this life cycle type process of looking at what will the change do in terms of introducing new hazards to the process or changing the hazards. Understand what those hazards are. Implement into your design means to manage those hazards, and then verify at the end of the design that you have indeed achieved the hazards management. The mechanisms by which we could do management of change, there's a lot of them out there, and that is a much bigger, and that's a topic in itself. How does 13849 differ from 61511? Those are for two different industry sectors. I think there's a lot of commonalities in what's required. Mostly they're tailored for specifics of that industry. 61511 is, of course, for the process industry like we see in chemical plants, where the requirements in nuclear are very different than they are in a chemical plant. And then, of course, in the automotive or machine sector, you've got continuously running machines, so there's different unit ops. So the standards are tailored a little bit for those kinds of unit operations that are characteristics to those industry sectors. How many years the functional safety verification or certification is valid? You should expect to see an expiration date on the certificates. When the certification is being done on a device, looking not only at the failure rate data, but in order to assess systematic capability, they're going in and looking at the operations of the facility, how the design and operations. And of course, those change over time. So you should you definitely expect to see a renewal requirement or an expiration date on those certificates to account for that evolution of design. Typically, I think you're probably talking 3 to 5 years might be common for most of these. Does exida maintain a library of various proof test procedures for different final control elements? We do have within some of our tools the ability to generate proof tests based on the design. That's kind of a variable thing because we end up putting different devices together. You know, a solenoid, an actuator, and a valve is a base assembly, but the requirements for proof testing depends from one model to the next. But there is something within the Excellentia tools to help us generate proof tests based on what the design is. Q1 correction is MOC management of change. Yes, it is. Let's see, I'm reading this one. If I understood, it seems to me that the execution and controlling and the smooth flow of executing the requirements of FMC is rigorous and tedious. Is the FMC and execution automated somehow in software format? If not, how do you make sure that the flow meters, checks, and balances to reach safe onshore and achieve your overall objective? Just to kind of rephrase that, I think you're asking how do you, is the process automated? Within the Excellentia tools, there certainly is a sequence of activities that connect the different documentation and phases that we use the Excellentia tools for through that life cycle that follows the requirements of a functional safety management plan. Of the safety life cycle, but obviously your functional safety management plan involves peoples and processes, and that's why we have the assessment stages that need to occur so that we can stop and check and make sure items that flow through the process, we verify and validate them at those stage gate activities, at those hold points, to make sure that everything that's happened up to that point achieves the overall objectives before we move into the next stage. So it's very important to do those assessments. People who were not able to attend, is this available afterwards? Yes, folks who've attended this webinar will get a copy of the slides. We also post on our exida website. All of our webinars are available there for folks. So if you go to exida.com, click under our resources, you'll be able to find the webinar page, and you can look up any of these and it'll be available for folks later. What degree of independence is recommended for the CFSP, CFSE in verification and validation of CIFs with a SIL 3 requirement? There actually, I believe, is some statements within the standard for a SIL 3. You want, certainly for those higher integrity systems, you want a higher level of separation between the people who do the design and do the internal verification and those that do the assessment. If you're going up to a SIL 3, you want more separation associated with that, and it's good to have more than one set of eyes on the process. For competency includes education, training, experience. How do you define how much experience? That's why we put these dossiers together, and it's looking at the kind of experience. Does an individual have 1 year experience doing the same thing 5 times, or do they have 5 years of unique experience? I can't put a particular number on it, but you've got to look at that overall package of the skills and the experience in order to determine, is that appropriate for the situation that you need them to, for the responsibilities that they're given. Proof testing should also link to the FDT calculations. I'm not sure what we mean. I'm not familiar with that acronym FDT. But if you're talking failure rate calculations, absolutely. Proof test coverage is part of those calculations. That's why we need to know what our proof testing capability will be early on in order to determine what proof test coverage is. The future seminars for the second and the third part, those will be available on the website when they're done. So if you happen to miss out on part 2 and 3, you can go to the exida website and pick them up later. Okay, I think I'm running into repeating questions at this point. So, and it's getting right up on 5 o'clock for folks. So I'm going to pause here. I thank you very much for your time and attention and joining on this session, and wish you a good evening. Thank you.